All right, we are back. It's Friday. We're trying to have a good weekend. Maybe Halloween will get in the way. Hopefully, OChem won't. We'll be okay with that. Um, yeah, we are finishing up chapter 9, though. So, homework 9 will be due tonight on Learning Suite. And we'll be starting chapter 10. We are moving along to alkenes, another chapter heavy in reactivity there. There is quiz 6. It's already posted on Learning Suite, and I think it's mainly alcohol reactions from this chapter 9. Data from test 2, very good. So there were a couple more almost perfect scores. We don't mind giving out hundreds. A couple people were very close, so that's very impressive. And overall, as a class, you're doing very well. So average of almost 80 there on this test, and test 2 does tend to be a little bit lower overall scores. I think test 1 was what, 83 average, so it went down to 79, but that's still very good. Again, if you're significantly below this average, there's some things you can do there to change your approach. Maybe come and talk to us, and we can help you out with that. A lot of it comes down to a matter of time, how much time you can put in to work the problems and go through things, but keep the principles straight. If there are some principles you're not following too well, make sure you come in and get some help and clear that up. There were a number of people who turned around their scores based on test 1. So I think there were 3 or 4 people who turned around their score by 14 or 15 points in the positive direction. And that's very impressive, even if the average of the test goes down a little bit. I love those turnaround scores. And there's always a number of you out there who are addressing that. So that's very impressive. All right, last time we did the dehydrations. Now we're going to do the halogenation reactions of alcohols. Alcohol is a very important functional group, of course, all over the place in nature, sugars, biomolecules, DNA, RNA. How we can transform alcohols into other products is a very important process. We'll also look at ether reactions today, especially epoxides. And let's see here. So halogenation, we're going to use HBr, HCl mainly. Tertiary is faster than secondary than primary. Tertiary and secondary, we'll get into the mechanisms, of course, are SN1 type mechanisms involving carbocations. Primary alcohols, though, can't go through a primary carbocation, and they'll tend to do SN2 type bimolecular reactions that avoids going through a carbocation. So again, use the mechanism to help you out here, but let's just look at the reactivity first. So here we have what a primary alcohol, 1-propanol reacting with HBr, and it cleanly goes to the primary bromide. So that level of understanding, reactivity, what conditions, what reagents gives what type of product. And here we have a tertiary alcohol, HCl, and what's going to be the product there? Well, the tertiary chloride. Okay. And if we got a secondary alcohol with HBr, we're going to go to the secondary what? Bromide. Okay. It's pretty straightforward. Again, tertiary alcohol here with cyclopentane structure and a methyl group on there. So that will go to that tertiary bromide. Okay. So far so good. Here's our first one where we see some issues with the mechanism, right? So here's an S alcohol, secondary alcohol. If we treat that with HBr, we're going to go to the bromide, sure enough. But is that bromide going to be the S or the R or a mixture of the two? What do you think? Well, I've already given you a hint, right? Secondary is going to go through a carbocation. So what do you say? How many people say it's going to be the S product? Okay, okay, a couple. How many people say it's going to be the R product? Oh, couple. You can't vote for the same one, can you? It's got to be one or the other. No. How many people say it's going to be a mixture of R and S? Oh, the vast majority. So very good. Just put the bromide there, and you can leave the stereochemistry undefined. You can draw both R and S, or you can just say DL, which is a way to say both enantiomers are there. So we'll see that come out in the mechanism. Let's look at a little more detail of that. So let's see. What will be the mechanism? Let's do this one. Tertiary alcohol, simple one, HCl, going to the tertiary chloride. So how would we start this reaction? Let's see if you can help me out here on the mechanism. Now, this is tertiary, so I already said it goes through the carbocation. But does that mean we just directly ionize off the hydroxyl group? No. What do we need to do first on the mechanism? Who can help me out? Tell my chalk what to do here. Go.
What I was thinking is the electrons on the hydrogen
Yeah.
are going to go to the oxygen.
Okay.
And create an OH2 on the
Okay. Yeah, how can we get OH2? We need to take the lone pair on the oxygen and do what?
Okay, it's the opposite.
Grab the proton. Okay, so yeah, the flow of electrons, the arrow is important. You have the right idea there. So I'd say that'd be our first step, right? And yeah, as pointed out, we get OH2. What do we call that? That has a plus charge now. That's hydronium ion. Just like protonated water, this is protonated alcohol, right? And then how do we get to the carbocation now? Now you can see we can form water and carbocation. Okay, everybody okay with that? Now, if it's tertiary, secondary, carbocation stable enough to make this pathway go. We call this, what, an SN1-like pathway, where it's just the ionization of this, just like we saw before with substitution. But now this is a better leaving group, right? So it's similar to that. And then what? Let's see, we still have chloride here. Or water could just go back on. That would be the reverse, right? Yeah. So how do we get to the product here? Well, it's pretty straightforward. Just go to that point. Okay. And you know, halide, that's all that's in there at that point. Water going backwards. To make this go faster, sometimes we add more HCl here, or you can distill off the water. So by Le Chatelier's principle, you can drive it over to the product. Okay, now because it's a free carbocation, we have an issue here with rearrangements. So let's see the rearrangements here that can come out of the mechanism. Let's see if we've got this type of an alcohol now, secondary alcohol, HBr. You might be expecting, well, we'll just put the bromide here, substitute for the alcohol. Guess what? That's not the product. We get 0% of that product. We get something else. Let's use the mechanism to see what that something else might be. We do have branching, right, at that beta position. And that branch point is going to do something what? Shift-wise. It's going to be one of those tricky, shifty reactions. So let's see. It's protonate. We're going to go to the hydronium ion, just like before. We're going to ionize the secondary carbocation. And like I said, bromide's not going on there. What else can occur? Should I give you the product, or can we figure out what the product's going to be? What do you think? This is what type of carbocation? Secondary? Is there a way we can do a shift from the branch position and get a more stable carbocation? The answer is yes. I'm seeing some head shaking. Do we want to do a methyl shift? We've got a couple methyls here. What else do we have, though? We've got a hydrogen. So how about a hydride shift? What would occur there? Let's shift this guy over here so we can get this. And as that hydride came over with its pair of electrons, this becomes neutralized, right? But what about where we pulled the hydride out of? What's the charge here now? Yeah, plus is right there. And notice that's a tertiary carbocation. So our product then is what? Not the secondary bromide, but this, right? So we can get the bromide there. And what do we have here? We have an ethyl on there. Okay. So again, look for branching. And if that's a possibility, or if we're next door to what? A small ring, we can also have that ring enlarge to do away with that angle strain that sometimes they have. So watch out for these shifts that can occur within that. Okay, let's see, we've got to do the mechanism for primary halogenation. So the one at the top there that we were doing was the HBr, and we got the primary bromine. Now, the mechanism starts out the same way, I think. We get hydronium ion, and notice that's a primary hydronium ion, right? If we tried to ionize that, it would be a very unstable primary carbocation. It wouldn't have the same inductive or hyperconjugation stabilization as secondary or tertiary. Well, what can occur here? Well, it's primary, right? And there's our nucleophile. So what do you want to do here? SN2 type reaction, right? Backside attack, directly on there. And that goes directly to the product, right? Because it is primary. Again, it's kind of back to the same idea in chapter 7. We've got to analyze the structure of the R group and what reagents we have here. The reagents are all the same. The HCl, HBr. Okay, some demos. I do have my white lab coat on for a reason today. Thank you. Oh, wow, he's bringing me money too. Look at that. Is that a dollar bill up there? I'm getting paid today or something? Look at that. Okay, there we go. All right. Our demo lab people, they're always helping us out. Okay. We'll see. We'll try to have some fun later today too. Question on this mechanism. Okay. It's because it is primary. It can't form. You don't want to do this. We'd have to take off points. Okay. So be very clear about, analyzing the R group here. This would be, 10 kcals per mole in energy uphill. This would not work. The bromide is there in proximity, right, just after it protonated here. And this is primary, so it's not hindered, right? Not like secondary, tertiary. And so this is able to do that. Okay, these are all strong acid conditions, right? HBr, HCl. HI also works if the iodide's stable enough. HF, no. Hydrogen fluoride is not a strong enough acid normally to do. The pKa of HF actually is only 3, okay? But HI is -9, very strong acid. It's kind of difficult to deal with. It's a gas and it's corrosive, whatever. So HBr, HCl are much more convenient there. There's another way to do halogenation reactions, and that's using this guy, thionyl chloride. Now there's a new name for you. The thionyl group is a sulfur with a carbonyl, you could say, and then 2 chlorides here. The sulfur is electrophilic. We'll see enough of the mechanism to see how this is useful. It's a very dangerous reagent. In water, this gives off HCl. It can damage the skin and the lungs. Very dangerous reagent. It is a liquid. We contain it carefully if we need to use it. But it is mild, at least reactivity-wise. There's no strong acid if you keep water away from it. So in that way, it's more mild on the rest of the molecule. If you have an acid-sensitive group or something in your molecule that can't tolerate strong acid, thionyl chloride's the way to go. So let's see, if you have a primary alcohol here with thionyl chloride, SOCl2, and pyridine is also added in there. So that's like POCL, the phosphorus oxytrichloride we saw before, where you have a base in there. And the base, pyridine, is just to soak up the proton off the alcohol. This will turn the alcohol into a good leaving group. Okay, so this isn't the whole mechanism yet. But you can see the product here would be a primary chloride. Let's look at a couple more here. If you got stereochemistry, so here's an alcohol, secondary alcohol, we're bold here, so that's what, S? And if you do thionyl chloride with pyridine, what's going to be the product? Well, it's going to be the secondary chloride. Let's see. It's going to be inverted, which is kind of cool. You can maintain the stereochemistry or invert it, really. Okay, so the stereochemistry went from went from S to, yeah, now R stereochemistry there. So, yeah, it also works with tertiary as well. But primary and secondary are the main ones it's useful for, especially primary, which is slow with HCl, okay, via the SN2 type mechanism, primary, carbocation not being available. But once you turn this into a good leaving group, and we'll see the mechanism, we'll go to the overhead, and you'll see how much better that can work there. Let's do the analogous bromination now under mild conditions, and it's not with thionyl bromide, although that reagent is known. The more convenient one is phosphorus tribromide. I don't need to write out the name, but phosphorus tribromide. Phosphorus is in the same row as nitrogen. It has 5 valence electrons, so there's a lone pair here, phosphorus tribromide. But this will take an alcohol and cleanly go to the bromide. Okay. And the other great thing about phosphorus tribromide is if you have branching next door, um, you know, where you might expect a shift or something here, with phosphorus tribromide, you know, with HBr, we get a shift there because we're branched at the beta position. But with phosphorus tribromide, again, we're not going through a carbocation. It will do brominations without any shifts. So you can even have one with 3 branch positions there. You know, it will cleanly give this. And let's have some stereochemistry here too. So here's a secondary alcohol with a lot of branching next door. But if you use PBr3, what do you get? You get the alcohol, or I'm sorry, the bromide. And let's see, is it maintaining this stereochemistry? That's R. So what do you get here? You actually get the S bromide. Okay. So it is with clean inversion there, just like the Tosyl chloride. So that can be very useful here. These reagents are very good, and it's quite fast, even with primary. So these are very good reagents to use. Let's look at the overhead here. Oh, and it is Halloween. Look at that. So we've got something scary to show you there. Yeah, people in class here have already been scared by that, but yeah, so some evil molecules here and some evil people lurking there. We got the big 3 illicit drugs there, which are certainly evil, you could say. We have Socrates up here. It goes back to the ancient Greeks. He poisoned himself with strychnine, right? And then we got Thriller going on here. Sorry, I don't have the music queued up. You can imagine that music or play it while you rewatch the video. And there's poor Michael Jackson. He passed away due to an overdose of this compound right here, Propofol, which is an analgesic compound, a very good one, by the way. Very simple compound, diisopropyl phenol, induces anesthesia and knocks people out for operations, whatever. It's also used as a sleeping drug, sleeping pill, but it can only be used in the clinic. He was using it at home and took an overdose of that and passed away. We got RU486, which kind of begs the question, are you for this molecule or not? Anybody know what RU486 does? It's an abortifacient drug. Okay, it's based on a steroid structure. We have synthetic marijuana here. Oh, we have sarin, the chemical warfare agent that this guy right here killed his brother-in-law with not too long ago. Very sad story. We got a terrorist here with a couple explosive agents. And then we got the Nazis here. Their drug of choice was methamphetamine, believe it or not. Okay. They gave it to their soldiers, actually, to stay awake indefinitely. And also cyanide. There's a drug compound the Nazis used. Yeah, some scary stuff here. But, you know, looking at all these compounds, which one's the number one killer year after year? Which one kills more people? I think I already mentioned it. Yeah, ethanol right there. There it is. Okay. Yeah, drunk driving, cirrhosis, and all sorts of bad health effects. Yeah, so scary enough. There we go. Okay, let's get off that quick. All right, let's see. So thionyl chloride, how does this work? Well, there's the sulfur, carbonyl, and the two chlorides. So yeah, that sulfur is electrophilic, we say. And the lone pairs you see are electron rich enough to want to attack that sulfur intermediate. I don't expect you to know this mechanism, so it's kind of like the Pockle mechanism. You don't need to know it. At least be aware of it, what's going on. It's turning the alcohol into a good leaving group, okay? Whereas before on its own, hydroxide's a terrible leaving group. And there's pyridines soaking up the acid and sequestering it. Now it's a very weak acid, okay? And then any nucleophile, including halides, chloride, is nucleophilic enough to do the displacement there. Give that. That operates for primary and secondary. If it's tertiary, it actually goes via an SN1 type thing. It ionizes first. So there's some little variations there you should be aware of. But secondary, if it's a stereocenter, it's cleanly what? Inverted, R to S, S to R. That's the key thing to keep track of with thionyl chloride. And plus, you don't start out with any strong acid, right? There's no HCl or HBr here. So it cleanly forms the leaving group and then converts it onto the alkyl halide. And the byproduct here is sulfur dioxide, which is a gas. So delta S for this reaction is very positive, and that helps make it more what? Exothermic overall, or exergonic, we should say. Contributes to the negative component of the free energy, delta G, Gibbs free energy, being a gas there. Okay, and then the bromide, phosphorus tribromide, PBr3 is similar here. We attack the phosphorus, form a good leaving group, and then, yeah, and then attack here. So primary and secondary go through that way and cleanly give the bromide, okay? And a phosphorus oxygen bond. Phosphorus has a high affinity for oxygen, phosphates, the most stable form of phosphorus, the oxidized form of phosphorus, phosphate in nature. You've probably heard of triphosphate, diphosphates, whatever. We'll see a lot of phosphates in biochemistry. Well, there's a phosphorus oxygen bond, which is very stabilizing. And that helps drive this reaction toward the bromide. Even though the carbon bromide bond is not very stable, right? It's a weak bond. If you look at the bond association energy, we're trading a stable carbon oxygen bond for a less stable carbon bromide bond. Why? Because we dump a stable oxygen phosphorus bond onto the byproduct, okay? You have to look at the whole change of bonding to get a feel for that. All right, I think that's okay. Here's a nice little review. The different reagents, yeah, so the reactivity, we did that, and we've done the phosphorus oxybromide and the PBr3. Yeah, HI can work. I kind of discount that because of the inconvenience of HI. It's just too strong of an acid, hard to deal with. And then a lot of times, alkyl iodide bonds are not stable. They're hard to isolate sometimes. But your book says it's useful for all alcohols. That's fine. And the mechanisms are similar to what we've talked about there. So I think that's okay. The next thing, oh, we'll do that later. But let's show another way to convert alcohols into good leaving groups. This is an important reaction here. It involves the formation of tosylates. So yeah, we got a couple new names here today, right? So let's see. Can we take some sort of a alcohol? Here I'm kind of accentuating it being a primary alcohol. You know, we can't do SN2 reactions directly there because OH is just a terrible leaving group, okay? Nature will turn these into phosphates. It'll phosphorylate those. You can also in the lab turn them into sulfates, okay? If you use this reagent here, if you use Tosyl chloride, and Tosyl chloride is this. It's sulfur with a couple double bonds to oxygen, and then this toluene group. We'll learn about aromatic groups later on. Tosyl stands for para-toluene sulfonyl chloride. So thank goodness for abbreviations there. Tosyl chloride. If we react that with pyridine, what we'll do is we'll form the tosylate. Okay, so we'll have that directly on sulfur. And yeah, we get tired of drawing out the toluene group and the sulfonate. So what this equals is what? This equals this, TS. OTS. And don't look in the periodic table, there's no TS element. It's an abbreviation for this large group here, the paratoluene sulfonate. And why is this important? Well, now all the charged nucleophiles can do their thing. Everything from chapter 7, right? This is now just as good as a halogen. In fact, tosylates are sometimes called pseudo-halogens, okay? They're stable, you can isolate those. They're often crystalline, so we can recrystallize and purify them. They're very convenient in the lab that way. And then you put in any type of nucleophile. Oh, what's your favorite nucleophile? Oh, let's look at acetate. Oh, how about sodium cyanide? And how about potassium azide? So all of these would be unreactive with the alcohol. But once we form the tosylate with tosyl chloride and pyridine, then we have what? Good reactivity. We can form the acetate ester. We can form the primary cyanide. Then we can form the azide and all the other ones there, okay? And remind yourself of the mechanism. These are good, what? SN2 reactions. And why? Because the byproduct here is O minus, okay? Toluene. Now, wait a minute. If alcohol was functioning as a leaving group, we'd also have O minus, right? We'd have hydroxide. But this is a different type of O minus, right? This is a sulfonate leaving group, right? And why is that possible? Well, this is resonance stabilized. In fact, you have a lot of resonance structures there, okay? This comes from Tosylates acid, which is a very strong acid like sulfuric acid. So this here is a very good leaving group, okay? Why? Because it's resonance stabilized, even though it's O minus, okay? It's different than just hydroxide coming out. So these tosylates can be very useful. Here's another reaction here. Let's do this one. If we react this secondary alcohol, what is that? That's S. We can react that with tosyl chloride and pyridine. And look, we'll get the S tosylate. And so the mechanism here forming the tosylate is the alcohol just directly attacking the sulfur. It doesn't change the stereocenter right there, okay? So it still stays as the S tosylate. And then if we do a reaction here, oh, let's do it with sodium acetate. We get what? We get the inverted product. We get the acetate ester, secondary, charged nucleophile, secondary, not very hindered, and what? We get the, wait a minute, is that the S? Wow, I got that messed up, sorry. I think these are R, correct? Okay, yeah, double check that. And this is indeed the S product, okay? So it goes with inversion, okay, once you convert that into a leaving group. But the initial stereocenter stays the same there. Let's look at a historical example of the use of tosyl chloride. In fact, this is a fundamental reaction that involves a biological molecule, lactate or lactic acid. And lactic acid is this compound here. We're going to look at the methyl ester of lactate. And this is one that's available in nature. So that's methyl lactate. It's got an S stereocenter there. Yeah, and if we treat this first with tosyl chloride and pyridine, look, we can form the tosyl lactate methyl ester, and we'll still have the same S stereochemistry there with that. And then if you take this and treat this with sodium hydroxide, and here's our charged nucleophile, secondary leaving group now, it inverts that. Gives an alcohol there. Now it's not, what, S anymore. It's now R. Oh, and also hydroxide will hydrolyze esters back to carboxylic acids. So now it's the R form of lactic acid. But to do the comparison here, they go back to the methyl ester with methanol and acid. Now, this reaction here is one we'll learn later, okay, ester hydrolysis. And this one here is ester formation. So we go back to the methyl ester there, but the OH group is inert to these conditions here. This is just a simple alcohol. Now, why is this an important reaction historically? Well, this S1 from nature is known, and they could take the optical rotation of that and see that it was minus 8.1 degrees rotation, lever rotatory. Yeah, the S is the lever rotatory one. And they thought, well, if we have a reagent that can do something to this stereocenter, yeah, they noticed they went back to lactic acid here. They converted it back to the methyl ester after that set of conditions, and they took the optical rotation again here. And what was it? Plus 8.1. Okay. Well, there's your equal and opposite rotations. Okay, this reaction was about 100 years ago, done by Walden. In fact, this backside attack, S to R to S, is called Walden Inversion sometimes out of honor for him. But it shows these biological molecules can be chiral. This is the first one that was fully characterized. Lactate that builds up upon glycolysis metabolism in the body. Lactic acid is also the burning sensation in your muscles if your metabolism's a little off there, if you're exercising heavily, whatever. But here they were able to show minus 8.1 and then back to plus 8.1. So this said something fundamental about this reaction, didn't it? Okay, so backside attack with inversion there. This is where this was first established and linked to the stereochemistry, the optical activity, using a biomolecule, this lactic acid. So even though you don't know these reactions here and here, you'll take my word for it, right? At least this one here, you know that one now, what's going on. But then the others, and then the comparison of the optical rotation. This is the L form, and here's your D form, okay? And that said something fundamental about how we got that stereocenter, okay? Yeah, other examples of it are fun. There's also other variations of the tosylate. There's a mesylate if it's just a methyl group and not that benzene. There's also triflates, which is trifluoromethyl, and maybe we'll show you some of that. All right, let's do ethers. And ethers will go pretty quick here. Um, acyclic ethers are generally inert to all these type of conditions, but some ethers can be reacted. In HI, let's use the really strong conditions here. Now, normally if we use diethyl ether or whatever as a solvent, it won't have a problem. But here we have a tertiary spot on this acyclic ether, butyl methyl ether. And if we use HI here, we get a couple products. We get the tertiary iodide, and then we eventually get methyl iodide if we have excess of this, okay? So how does this mechanism go? Well, we can protonate the ether and get the hydronium ion, okay? And then you see we got this tertiary spot here. So that'll give us the carbocation plus methanol, okay? Methanol alcohols are sometimes the products here. And then how do we get the iodide? Well, there we go. I minus is floating around in there. Okay, how do we get the methyl iodide from methanol? If we just stop with one equivalent, those are the two products. But if we have excess, what can we do here? Well, we can make more hydronium ion, right? Just a methyl on here. And then I can attack here. And that's what? SN2 type process, because it is primary there, right? So can attack there and flow the electrons here and lose water and form that. This is not preparatively useful. This is really a degradation type reaction where we're breaking apart a functional group and going back to two organic fragments here. So you can see synthetically it's not very important or very useful. In fact, most acyclic ethers, like diethyl ether, we don't need to worry about that as being reactive in a lot of reactions. In fact, we can use it as a solvent for most of these reactions. Why? Because that would be primary carbocations, okay? And other things are more reactive. So these acyclic ether reactions, don't worry about it. Well, let's get to the epoxide reactions now. Now, epoxides are also ethers, right? But they have three-membered rings. Okay, so epoxides. And you played around with epoxy resins probably, and I'll show you that reagent here in a second on the overhead. These epoxy compounds are ethers, but the three-membered ring, well, we have the angle strain, right? This theta thing constrained to be 90 degrees. That wants to break open. And when it breaks open, that releases about 30 kcals per mole. So these are actually reactive with your standard nucleophiles, okay? They can attack here and break this little ring open, which is kind of a cool thing. Let's look at a reaction here with sodium methoxide. Well, that's one of our SN2 nucleophiles, right, from chapter 7. You can do this reaction here in methanol. And what will be the product? The product will be this. Now, that's a highly functionalized molecule. It's got 2 oxygens on it. One is an ether, one is an alcohol. And notice the ether is at the primary position, and the alcohol ended up at the secondary position. So how does this work? Let's see. First of all, what's this position? That's a primary position, right? That position is a secondary position. So all the principles apply that we talked about with charged nucleophiles, right? Where is this nucleophile going to want to attack? Well, right here. And when it does it, our leaving group is O minus in this case. I've been saying the whole time, O minus is a terrible leaving group, unless there's something else there, like a tosylate or whatever, or if it's protonated first, right? Hydronium. It's not hydronium ion. This is basic conditions, okay? Charged nucleophile. It's this angle strain that's allowing this to pop open like that, okay? So it's a little bit different mechanism, a little different concept. You could say same mechanism there, the SN2 attack. So we'll have O minus here and OMe right there, okay? So we're already almost there, right? And don't worry about that O minus. We're under basic conditions, so this is okay. But look, we just gained 30 kcals per mole by popping open that ring. Now it's relaxed. Now it's all 109.5, right? So this is why this can work. And how do we get to the product? Well, we are in methanol, so we just grab a proton off methanol and go straight to that, okay? Now, let's compare this reaction, same substrate, but let's do it in acid, H2SO4 in methanol. Okay, same epoxide. What's going to occur here? Well, we can protonate the ether oxygen of the epoxide first. So different mechanism. We're under strong acid conditions now. Here's our hydronium ion of the epoxide. And what's going to occur now? Notice our nucleophile is neutral now, right? It's methanol. It's not methoxide like before. Okay, this was basic condition. Here under acid conditions, right? So here's our intermediate. What's going to happen there? Okay, here's our primary position. Here's our secondary position. This epoxide is going to want to open up on its own now. This is more of an SN1 type reaction. So which side's going to open up? Is it going to open up and form the primary carbocation or open up here and form the secondary carbocation? Secondary, yeah, we didn't need to vote there. Everybody chimed in with secondary right away. So let's do that. And what do we get there? We get a secondary carbocation. And look, we get an alcohol now at the primary position. Okay. We've already switched our positions here. And now what? Let's see, what can attack here? Oh, we got methanol. There it is. Methanol goes on there. We'll have the methyl ether hydronium ion. And notice the methyl ether now is at this 2 position there. And then what? Let's see, we've got more methanol. Or we can use bisulfate. We started out with that. We can grab that proton here. And what do we get? We get this product, right? We get the ether at that spot, okay? And we get the alcohol at the primary position. We've just switched the groups here, right? Under basic conditions here, we got the methoxide at the primary position because that's our charged nucleophile. Okay, so what are we going to say here? We say we get complementary type of selectivity here. This is an issue of regioselectivity that we'll see a lot of coming up here in chapter 10. Which region of the epoxide got functionalized? Well, here, the nucleophile went to the primary spot. Why? Because we're under basic conditions with methoxide. Here, though, we're under acidic conditions, and we go via the more stable carbocation, okay? And we reverse this selectivity, okay? So it's complementary conditions here. Let's work a couple more of these, and then we'll go back to the overheads and try to do some demos here. Yeah, question on this. Yeah. So the proton on the longer chain, the key here under basic conditions is the nucleophile goes to the less substituted spot, the more sterically available, the sterically unhindered spot. And that is the primary position, right? So that's why that went on there. And then the O minus just grabs a proton from the solvent, the methanol. Yeah, because the O minus is never here, okay? Because the nucleophile can't attack selectively at a secondary spot, okay? So you see the nucleophile attacks here at the primary position and opens it up. So you get the O minus, you see, at that secondary spot. So if you follow the mechanism and think about the steric approach of a charged nucleophile, it's going to want to go primary. Yeah, and that's the reason. Let's work a couple more examples, and I think this will make some sense. And what do we got here? How about this one? So here's one where we've got epoxide. And that epoxide has what? A secondary position and a tertiary position. Let's do the one here where we're reacting it under sodium methoxide conditions in methanol. Okay, and let's do the one where we're reacting it under acidic conditions in methanol. So the solvents is the same, methanol, but here we have the methoxide charging file. Here we just have acid. And so what are we going to form here? Well, this is going to attack here, backside. Going to invert that position. The alcohol is just going to get protonated. So the tertiary stereocenter stays the same. And what? Here we get OME with that down now. Okay? Backside attack. And the OME goes to the less hindered spot, secondary in this case. And the alcohol winds up at the more hindered spot. And then this one's just the opposite. So we get the approach here where we protonate. And OME goes here. And alcohol goes there. And notice I'm drawing the stereochemistry undefined here. It actually gives a mixture of diastereomers. This stereocenter stays the same. So this isn't DL now. This is a mixture of these two. And you can see how that arises. You go through the rest of the mechanism. So one is that. And the other one's that where that stereocenter is the same. But what? You have OME down and the methyl up. And why is that? Well, you've got hydronium ion now that forms what? A flat carbocation. And when it opens up, you see that stereocenter is the same, but then this one, see, it's flat. So methanol can attack from the top and give this one, or it can attack from the bottom and give this one, okay? So yeah, we'll review that, and we'll review a bunch of reactions on Monday. Let's go to the overheads again here. I think we got a minute, couple minutes. Pockle doesn't always do eliminations. Here's our dehydration conditions. And in this case, actually, this tertiary alcohol, tertiary chloride, turns out to be a major one. Sometimes it's mixtures, and actually Pockle is best for secondary alcohols. That's where it cleanly goes to alkenes. Tertiary alcohols sometimes give a lot of substitution because of carbocation stability, or they give a lot of, with primary, they give a lot of halides also, and that's because the SN2 pathway becomes operable. It's really better with secondary. Here's one where it's all substitution, but that's a tertiary alcohol. So some other things that Pockle can do. Here's our Tosylate leaving group, just the rest of the details of that, how it's formed. We retain the stereochemistry forming the Tosylate, but then when we react it, right, with the SN2 reaction, it does get inverted there. So here's a couple examples. Here's a chiral alcohol that's S. And let's see. Here we're putting on a mesylate group. That's like a tosylate. It has a methyl group there. And then here's our charged nucleophile. This carbonate base can take the proton off the sulfur. And then the backside attack, yeah, inverts that stereochemistry right there. And that's Singulair, another asthma drug. A couple other SN2 reactions here. Oh, there's one with a mesylate, which is again similar to the tosylate, forming a primary mesylate, and then cyanide displacing right there. Yeah. Oh, and here's an epoxide opening. So other good nucleophiles are the amines or ammonia, right? Even though they're neutral, they're like the SN2 nucleophiles. There's a secondary amine opening up this epoxide right here and making that bond right there. And why? That's the primary position. That's where a good nucleophile would want to attack on its own. This is not acidic conditions, nucleophilic conditions to give that. And there's a Ceravent product. Same thing here with this one, with the tertbutylamine, opening up the epoxide right there, forming that bond. Okay. Yeah, and those are those two different asthma drugs that we've talked about before. Epoxides in nature can be opened up by different types of nucleophiles. This is one in the leukotrienes, which are similar to the prostaglandins, and the sulfur is attacking right there. That's done with an enzyme, though. Here's the one I talked about that's the carcinogen in cigarette smoke that causes lung cancer. This comes from soot, from anything that's burning, by the way, including campfires, not just cigarettes. But this benzopyrene is a soot-type molecule. It gets oxidized in the liver to this epoxy dialcohol, and that epoxide can react with DNA. And it actually alkylates DNA, causes a frame shift, which leads to a mutation in this tumor suppressor gene. So this protein gets expressed incorrectly, and it can't suppress cell turnover. And it leads to uncontrolled cellular turnover or division, which is a hallmark of cancer, right? So if that happens in a subset of cells within the lungs, that can be a big problem. So there's the whole story. Luckily, you only get a tiny amount per cigarette. Nanograms is tiny. But if enough gets in there, and this oxidation occurs in the liver first, and then you see the DNA can open up that epoxide and lead to this alkylated soot molecule, which intercalates into the double-strand DNA and leads to a frame shift. And if that mutation occurs in P53, that's a tumor suppressor gene, which forms a protein that stays on DNA and keeps it from unwinding and duplicating. That leads to uncontrolled cell division. This is the most well-established, detailed approach to how cancer arises at the molecular level, okay? And it proves why cigarette smoke is not good for your health, okay? A lot of other things with cigarettes, right? Emphysema and other things. All right, let's do a couple demos here, and I don't know if we got time, but maybe we'll just do the burning dollar one here. Alcohols do burn, and let's see. So here's pure ethanol. I'll put a little of that on it. Let's see if it burns. Yeah, it does burn. There you go. Burning alcohol. That's 100% alcohol. Here's ethanol water. So this is 100 proof. This is 50-50 water, ethanol. Put a little there. We'll see if that burns. Burns a little bit, but certainly not as much as the pure ethanol. There's the difference between 200 proof alcohol, pure alcohol, and 50/50. Let's take a dollar bill here and put it in the 50/50 and see if it will burn. Now, I'm actually breaking a federal law right now. I'm defacing the currency. Oh, but that's 50/50 water alcohol. Of course, water doesn't burn, right? Let's do that again. How come it didn't all burn up? Let's see. Burns off the alcohol, but look at that, the dollar bill stays fine. Okay. Should we do the dollar bill in pure alcohol and see what happens? Okay, remember this is the pure alcohol over here. Let's get that burning. And I'm going to put pure ethanol now on our dollar bill. And hopefully I won't catch myself on fire. Uh-oh. Now I'm really violating federal law. And don't tell your parents about this either. They don't need to know that we're burning money at BYU. They probably already think that already, right? But okay, so why is it burning completely now? Combustion's fully supported there. Alcohols do burn. There's probably a little bit of water still in the fibers of the dollar bill, but that's burning up now, right? So yeah, that's the difference. 100% ethanol being very flammable, right? And what do we have? 50/50 here. Should we do that one again? That one hardly burns at all. Believe it or not, this is where the idea of proof comes from the pirates in the Caribbean, believe it or not. Pirates of the Caribbean, there you go. How did they prove that their rum wasn't watered down? They'd pour it out on the deck and light it on fire. If it burned very well, that was not watered down. If it was watered down, it didn't burn as well. And there was the proof, okay? So there you go. There's a little Halloween thing. Don't try this at home, okay? It's not good that way. So very good. We'll see you next time. Chapter 10 coming up. Thank you.